So imagine walking into a production review at, a really state-of-the-art manufacturing facility.
Right. You've got your coffee, you're finding a seat at one of those massive oak tables.
Exactly. And you look up at the screen at the front of the room, the dashboard is just glowing, and every single key performance indicator is green.
Ah, the dream scenario.
Right. I mean, average cycle time is running at this perfect 14.2 seconds. Average machine utilization sits comfortably at 88%.
Which is great.
It's fantastic. Average defect rate is hovering at a negligible 0.02%, and average throughput is flawlessly tracking at 1,200 units per hour.
So the executives in the room, they're relaxed.
Yeah, people are nodding, hands are being shaken.
Exactly. The meeting ends 20 minutes early in this state of just quiet professional confidence.
Because it looks like the ultimate illusion of perfect systemic health. Well, that's exactly what sets up the inevitable fall.
Yeah, because 45 minutes after that meeting ends, the entire factory just goes quiet.
Yeah, the constant, that underlying low-frequency rumble of production simply stops. Red lights start flashing all above the floor.
Let me guess. A single CNC milling machine.
Exactly. A critical CNC milling machine has suffered a catastrophic mechanical shear. A spindle literally locked up at 10,000 revolutions per minute, completely shattering a cutting tool.
Wow. And I'm guessing it destroyed whatever part was in there.
Oh yeah, destroyed a $500,000 titanium aerospace component. Gone.
Right.
And the postmortem reveals that it didn't just suddenly break out of nowhere. It had been, quietly drifting out of tolerance, vibrating at an abnormal frequency for like 3 weeks.
3 weeks.
3 entire weeks. So we are left with the defining mystery of our deep dive today for you listening. What did the dashboard know that the factory didn't? Or, perhaps more accurately, what did the factory know that the dashboard simply couldn't?
I love that framing. Because that tension, that gap between the screen and the floor, is arguably the most fundamental problem in modern systems engineering. We're really looking at a profound disconnect in how human beings, and particularly how modern organizations, observe reality.
Because the data wasn't ignored, right?
Exactly. The thesis we have to explore today is that the data in that factory wasn't ignored at all. The sensors on that spindle were collecting gigabytes of vibrational telemetry every single hour.
Nobody falsified the reports?
No, nobody manipulated anything. The data was there, but it was subjected to an operation that organizations perform every single day. It was averaged.
And that's the trap.
It's a huge trap. The inescapable truth of complex operations is that systems almost never fail at the average. I mean, they fail at the exact observations that the average quietly erased.
Which brings us to the actual physical nature of failure itself.
Yeah.
Let's look at what is actually happening at the metallurgical level when a machine like that breaks down.
Right, down in the physical world.
Yeah, because if you spend enough years walking factory floors, you start to recognize this fundamental truth. Reality is surprisingly generous.
Generous is an interesting word for it.
Well, it is. It almost always whispers long before it shouts. I mean, a production line does not spontaneously collapse overnight without leaving a trail of breadcrumbs.
No, you see this across every physical discipline. Think about an industrial bearing supporting a massive rotational load. Weeks before that bearing actually seizes up, the microscopic imperfections in the steel begin to generate friction.
And that friction creates a signal.
Exactly. It produces a faint acoustic signature, perhaps a shift in the high-frequency vibration from 12 kilohertz to 12.5 kilohertz.
Barely noticeable, but it's there.
It's there. And then a few days later, the thermal profile changes. The casing warms unevenly, maybe by just 2 or 3 degrees.
Right. Or look at that CNC machine we just mentioned. The tungsten carbide cutting tool slowly wears down by a fraction of a millimeter. And as it wears, the machine has to draw slightly more electrical current to, push that dulling tool through the metal.
Physics is constantly broadcasting these anomalies. I mean, the machine is practically begging for an intervention.
Wait, I have to challenge that premise, though. If reality is so supposedly generous, right?
Yeah.
And physics is constantly broadcasting these warnings, why do things still break suddenly all the time?
That's the million-dollar question.
I mean, I have seen heavy machinery snap with zero apparent warning. If the clues are always there, why is our default state to build systems that actively hide them? Why do organizations crave the tidy number so much that they systematically blind themselves to the whispers?
Well, the suddenness you experience, that's not a failure of the machine to broadcast. It's a failure of our observation scale.
How do you?
The clues are there, but they exist at a frequency or maybe a granularity that our reporting mechanisms are explicitly designed to filter
Oh,
out.
I see, because of scale.
Right. Organizations require simplification to function at scale. A chief operating officer cannot look at the real-time, fast Fourier transform charts of acoustic vibration data for 10,000 individual bearings.
The cognitive load would just be impossible.
Exactly, it would break them. So the organization demands a summary. They demand a dashboard. And the most common tool we use to summarize massive data sets is the arithmetic mean.
So we take all those micro fluctuations, all that acoustic data, the temperature spikes, the current draws, and we just mathematically flatten them.
We flatten them completely.
Averages are beloved by organizations because they're just incredibly tidy. They fit perfectly into quarterly summaries. They make benchmarking between different facilities mathematically simple. And they provide executives with this profound sense of control.
But the danger is that this control is entirely an illusion, and it's bought at the direct expense of vital information.
Yeah.
The dashboard you described in that production meeting represents a deep structural contradiction. It's the tidy, frictionless dashboard sitting on top of an inherently untidy, high-friction physical reality.
It reminds me of the classic thermal analogy, the
The
one.
feet in the water.
Yes. If you have one foot in a bucket of ice water and your other foot is in a bucket of literally boiling water, the average temperature suggests you are having a surprisingly comfortable afternoon.
Right, statistically, you're perfectly fine.
But reality is going to file a very different report with your nervous system.
It's absurd, but it's exactly what we do. And you see it in healthcare, too.
Oh, right. Imagine a hospital proudly putting out a press release saying, our average patient is perfectly healthy.
Exactly. How does the single patient coding in the intensive care unit feel about that analytic?
Probably not great.
Probably not. It really highlights the absurdity of applying central tendency to complex, high-stakes environments. And the thing is, the dashboard wasn't lying in your factory example.
Right, nobody was cooking the books.
Nobody manipulated the reports. The dashboard simply answered a question that nobody should have asked in the first place.
So to really understand why the dashboard fails the factory, we have to look at exactly what mathematical operation we're performing when we hit that average button.
Yeah, we have to look at the mechanics of it. And to understand that contradiction, it really helps to look at how audio engineers handle digital compression.
Oh, the MP3 analogy. I love this one.
It's perfect. When you take a high-fidelity studio recording this massive WAV file with incredible sonic depth, and you compress it into an MP3 file to make it easier to stream, you're running a mathematical algorithm that permanently deletes data.
Right, because it has to make the file smaller.
Exactly, and the algorithm specifically targets the highest and lowest frequencies, the variations that it assumes the average human ear simply won't miss.
So it's making a judgment call on what's important.
It is. It uses psychoacoustic masking to hide those deletions.
Yeah.
So the file becomes infinitely easier to transmit, which is great for this streaming service.
And then an audiophile, who is essentially the equivalent of our manufacturing engineer, puts on high-end headphones.
Right. And they immediately realize that the depth, the texture, and the actual reality of the music have just been destroyed. The average is the organizational equivalent of MP3 compression.
That is such a good mechanistic analogy. Let's walk the listener through the actual sequence of how an organization processes reality, because there are really 4 steps here.
Yeah, let's break it down. Step 1 is observation. The sensor physically detects the heat or the vibration.
Okay, then step 2 is measurement. That observation is converted into a distinct quantitative data point.
Right. Step 3 is compression.
Hmm.
You take millions of those data points collected over a month, and you apply a mathematical function.
And step 4 is the average. You are left with a single, highly compressed number. You've made the reporting fast, the PowerPoint slide is super legible, but just like the MP3 file, you have permanently deleted the extremes.
You've deleted the extremes.
Yeah.
And in the context of an industrial system, or really any high-stakes environment, we have to ask, what exactly are we leaving on the cutting room floor during that compression?
We are deleting the outlier. We are deleting the anomaly. I mean, when you calculate an average, the mathematics take thousands of perfectly normal, safe observations, mix them with a handful of highly abnormal, dangerous observations, and just blends them until the danger is invisible.
It politely escorts the most critical data right out of the room.
It really does.
I want you to picture an immaculate, brushed aluminum inspection table in a metrology lab.
Okay, I'm picturing it very clean.
Very clean, museum quality. Sitting on that table are 20 precision-machined aluminum cylinders.
Right.
Now, 19 of those cylinders are machined to exactly 10,000 millimeters. They are flawless.
Perfect parts.
But one cylinder was machined with a worn tool, and it measures 10.0050 millimeters.
Oh, wow. That's a massive defect. That's going to cause whatever assembly it goes into to bind up and fail.
It absolutely will.
Yeah.
But if you run the average dimension of those 20 parts, the math returns 10.00025 millimeters.
As a minimalist digital dashboard hovering above that table calmly reads, average dimension. Perfect. Or, well within acceptable tolerance.
Exactly. The dashboard represents the summarized, compressed knowledge, but that single out-of-tolerance cylinder represents actual reality. The dashboard cannot see the defect because the mathematics of central tendency explicitly blinded it.
The dashboard is completely happy, but the engineer standing at the table is reaching for a micrometer.
Because the engineer knows better.
They know that the information that was compressed away, that 0.0510 millimeter deviation, has a specific name in engineering. And honestly, it is the hidden hero of this entire discussion.
It really is.
We are talking about variation.
Variation. We need to completely reframe how organizations and how you listening to this view variation.
Because it gets a bad rap, doesn't it?
It has terrible PR. In standard corporate finance or high-level operational reporting, variation is treated as a nuisance.
Yeah, it's just a mathematical inconvenience that makes your charts look messy and unpredictable. It refuses to cooperate with the quarterly summary.
Right. But in systems engineering, variation is treated as hidden information. It's not a nuisance. It is the most valuable commodity in the room.
Because somewhere inside every average is a distribution. And somewhere inside every distribution is variation. And somewhere inside that variation is tomorrow's catastrophic shutdown, arriving a few weeks early with, excellent manners, politely waiting to be noticed.
It's knocking on the door. But like we said, outliers have terrible public relations. They ruin the efficiency of a meeting.
Oh, absolutely. If you bring raw distribution data showing massive variance into a board meeting, it forces the whole room to stop. People have to ask questions, they have to investigate.
Which leads to a core principle of restorative engineering. When everyone else in the facility is standing around admiring the glowing green dashboard, the experienced engineers are quietly wandering out to the actual machine.
Right.
When everyone is celebrating the average KPI, the engineers are the ones asking, hey, can I see the distribution?
I have to push back here, though.
Go for it.
I have sat in those boardrooms. I've presented to those executives. If I walk into a quarterly review with a CEO and I completely bypass the average KPIs to present raw, uncompressed distribution models of acoustic sensor data, I am going to get laughed out of the room.
Well, yeah.
Executives do not have time for raw variation. They have thousands of employees, global supply chains to manage. So aren't averages a necessary evil? Like, how is an organization actually supposed to function without compressing this data?
You're touching on the essential divide here, which is the difference between navigation and control.
Navigation and control. Okay, break that down.
The executives need the average to navigate the macro direction of the company. It's a necessary abstraction for resource allocation.
Right, they need to know if the ship is generally heading north.
Exactly. The failure occurs when the organization begins to believe that the abstraction is the reality. The CEO should absolutely use averages to decide which factory needs more capital investment.
Yeah.
But the plant manager and the reliability engineers, they cannot use those same averages to run the physical systems.
So the danger is not the existence of the dashboard. The dashboard is fine for what it is. The danger is the assumption that a metric designed for executive navigation is somehow suitable for systemic control.
Precisely. And that distinction, navigation versus control, allows us to bridge this concept way out of the physical factory.
Because this mathematical phenomenon of erased clues isn't just a manufacturing problem. It scales perfectly to the digital world, to digital systems.
It scales to logistics, to software, to everything we build. The shared mechanism of failure is always the math blinding us to the tail of the distribution.
Let's look at some cross-domain examples, like logistics and queuing theory.
Oh, this is a great one. We can trace this exact mathematical failure through a global delivery network.
Right. Imagine a massive national network. The monthly dashboard reports that the average delivery time across the entire network has improved. Let's say it went from 48 hours down to 42 hours.
The executives are popping champagne.
The dashboard is celebrating. But queuing theory, specifically formulas like Kingman's equation, tells us a very different story about variation.
Kingman's formula is brutal. It dictates that as a system's utilization approaches 100%, the wait time doesn't scale linearly. It scales exponentially based on the variation in arrival times and service times.
Let's break down the physical mechanics of that for the listener. If you have 50 regional distribution hubs, 49 of them might be running slightly below maximum capacity. They're processing packages smoothly.
Everything looks great on average.
But one specific hub has quietly invented its own time zone. It has pushed its utilization to 99%. And because of natural variation, maybe 3 massive delivery trucks arrived at the exact same time instead of being staggered throughout the hour. The queue at that single hub just explodes exponentially.
Packages start literally piling up on the floor.
Exactly. The bottleneck is real.
And the overall network average pulled the math down, completely hiding the localized collapse. The dashboard is celebrating a 42-hour average, while the queue in that one specific hub remains professionally committed to existing.
It's locking up thousands of packages and preparing to send this massive ripple of delays across the entire country.
The average hid the localized failure until it was way too late.
And that bottleneck in the logistics hub isn't just a physical queue of cardboard boxes. It's the exact same mathematical phenomenon we see in cloud computing and software engineering.
Absolutely. When a massive server farm gets overloaded, we are dealing with the exact same equations.
Right. A software platform might look at their monitoring tools and celebrate an average server response time of 120 milliseconds.
Which, in the software world, is blazing fast.
The dashboard is incredibly green.
But again, we have to look at the distribution. We have to look at what software engineers call the tail latency.
The P99 tail.
Right. In a complex microservices architecture, a single user request might trigger hundreds of internal server calls. If we look at the 99th percentile, that P99 latency, we are looking at the slowest 1% of requests.
And that's where the pain is.
It is. While the average is 120 milliseconds, that P99 tail might be taking 10 full seconds to resolve.
And in software, you have to ask yourself, who actually exists in that slowest 1%?
Usually not the casual users.
No, it's rarely the lightweight anonymous user just loading the homepage. The P99 tail is almost always your enterprise clients.
Of course.
They're your power users. They're the ones running massive, complex database queries. So while your executive dashboard is celebrating a 120 millisecond average, your most valuable, highest-paying customers are experiencing software that is effectively broken.
The mathematical average is quietly teaching your best customers exactly where your competitors live.
Such a dangerous blind spot.
Yeah.
And we see this exact translation of risk when we analyze artificial intelligence, too.
Oh, AI is fascinating here because AI is fundamentally a statistical optimization engine.
Right.
During training, the algorithms adjust their weights to minimize a loss function, and that loss function is almost always an average, like mean squared error or average cross-entropy loss.
So it's literally built on the concept of the average.
It is. Let's say a newly deployed AI model proudly reports a 98% average accuracy rate. I mean, for a university exam, that's an A+.
But wait, I have to play devil's advocate here. An AI model doesn't have physical constraints. It doesn't have a queue of cardboard boxes, and it doesn't have a physical bearing that warms up and wears down.
Yeah.
So how does the concept of physical variation apply to code running a neural network?
That is a great question. It applies because the math of the loss function maps exactly to the math of the average. The AI optimizes for the center of the distribution, which is where the bulk of the training data lives.
So it gets really good at the normal stuff.
It learns to perform exceptionally well on normal, expected inputs, but it sacrifices performance on the edge cases, those rare, highly variable inputs that live out in the long tail of the distribution.
And in many critical systems, that remaining 2% of inaccuracy isn't just harmless statistical noise.
Not at all. It contains every single safety-critical edge case that your legal team will eventually be asking you about.
That makes total sense. Imagine comparing 2 different AI models for an industrial application. Both proudly boast a mathematically identical 97% average accuracy. The first model is used for optical character recognition on handwritten invoices. When it hits its 3% error rate, it occasionally misclassifies a number, requiring a human clerk to manually retype it.
It's annoying, it slows things down, but it's operationally manageable.
Exactly. Now consider the second model. It is deployed to monitor the acoustic telemetry of a deep water drilling rig. It also has a 97% average accuracy. But when it fails in that 3% tail, it confidently misclassifies the early acoustic resonance of a catastrophic high-pressure valve failure as, normal background ocean noise.
Oh. Yeah, the average performance of those two models is absolutely identical, but the engineering consequences couldn't be more different. I mean, they're separated by hundreds of millions of dollars in human lives.
Because metrics describe the system, but the context of the variation decides the reality.
That is perfectly said, and it brings us to the core philosophy of structural and reliability engineering.
How so?
Think about how civil and mechanical engineers actually design physical infrastructure. They do not design for reality as it exists on an average day. Oh, that's so true. When an engineering firm designs a suspension bridge, they do not calculate the average wind speed of the valley over a 12-month period and build a bridge to withstand a 10-mile-per-hour breeze.
The bridge would collapse in a week. No, they study the historical distribution of weather patterns, they find the extreme tail of that distribution, and they design the bridge to survive the once-in-a-century wind shear.
The exact same principle applies to aerospace. Commercial aircraft wings are not certified by the FAA to fly through average atmospheric turbulence.
No, during testing, they are subjected to catastrophic wing-up bending tests. They place them in these massive rigs and bend them upward until the internal aluminum spars literally snap.
Just to prove they can survive loads far beyond anything they will ever normally encounter.
Exactly. Pressure vessels are tested to catastrophic yield, not average operating pressure. Industrial robots are validated against their maximum possible positional error, not their typical accuracy. Because engineering has never, ever been interested only in normal behavior. Engineering exists entirely for the moments when reality stops being normal.
Which forces us to define a really profound distinction here. We have statisticians and we have engineers.
Right.
They can both look at the exact same data set, the exact same spreadsheet of numbers, and draw entirely different conclusions. So what is the core difference in how those two disciplines observe reality?
The quiet difference lies between measurement and understanding. Statistics, by its very nature, exist to summarize data to help us describe a system.
It asks the question, what usually happens?
Exactly. Whereas engineering investigates data to help us understand the physical mechanisms of the system, it asks us a completely different question. What is beginning to happen that shouldn't?
Those two questions create remarkably different organizations, and we can trace this exact engineering philosophy back to the 1920s at Bell Labs.
Oh, Walter Sheeher.
Yes, Walter Schubert. He was a physicist tasked with improving the reliability of underground telephone transmission systems.
And at the time, quality control was purely reactive.
Completely reactive. You measured the average number of defects at the end of the line, and if the average went up, you basically yelled at the factory workers.
Which is mathematically illiterate.
Completely. Schubert realized that every process, no matter how precise, has natural built-in variation.
He recognized that if you react to every tiny variation, you end up over-adjusting the machinery, which we call pampering, and that actually introduces more variation and makes the system worse.
Right, you're constantly chasing your own tail.
But on the flip side, if you react to nothing, assuming it's all just the average cost of doing business, you miss the critical failures.
So he needed a mathematical filter, something to tell him when variation was just random background noise, and when it was a quiet signal that reality had stopped agreeing with the dashboard.
And his solution was the control chart, the absolute foundation of statistical process control, or SPC.
SPC is brilliant. Explained without the math, Shewhart essentially used standard deviation to calculate the natural limits of a process. He plotted the data and drew an upper control limit and a lower control limit, usually 3 standard deviations from the mean.
And he created a rule for deploying human attention, which I love.
Yeah, what was the rule?
Ignore everything inside the limits, because that is common cause variation. That is just the normal hum of the universe.
Right.
But the microsecond a data point falls outside those limits or trends in a specific non-random pattern, you stop the line and investigate immediately. That is special cause variation. It means the physical reality of the system has fundamentally changed.
That is the essence of control.
I want to share an observation from a mentor of mine that really brings Shewhart's math to life in a visceral way.
Please do.
This mentor was an older manufacturing engineer overseeing a massive automated assembly line. And one afternoon, he was looking at the real-time SPC charts on his monitor. He wasn't looking at the X-bar chart, which tracks the average. He was looking at the R chart, which tracks the moving range, the variation between consecutive parts.
Okay, so he's looking at the spread.
Exactly. He noticed a tiny, almost microscopic upward drift in the variation of a specific robotic fixture.
But the average dimension of the parts coming off that fixture was still perfectly green.
Yes, the dashboard in the executive suite was still indicating a flawless production day. That is the insidious nature of the average.
So what did the rest of the team think?
While the young technicians in the control room dismissed the drift, they assumed it was just sensor noise or maybe thermal expansion from the afternoon heat. But this mentor understood that sensors sample at specific rates, and when you see a rhythmic drift in the variation, you're often looking at a harmonic resonance.
Oh man, he knew something physical was happening.
He spent 2 hours tracing that tiny blip. He completely shut down the cell, locked it out, and climbed inside the machine with a flashlight.
What did he actually find?
He found a single heavy-duty mounting bolt that had backed out by perhaps an eighth of a turn.
An eighth of a turn.
An eighth of a turn. It wasn't broken. It was just loose enough to alter the resonant frequency of the massive steel fixture holding the parts. The cutting tool was hitting the metal, and the fixture was vibrating on a microscopic level, creating that tiny increase in the variation of the final dimensions.
So he just tightened it?
He took out a torque wrench, tightened the bolt in about 20 seconds, and turned the machine back on. The variation on the R chart completely vanished.
Wow. If he had trusted the average, what would have been the mechanism of failure?
Well, the vibration would have continued to back that bolt out. Over the next 3 weeks, the mechanical slop would have increased until the bolt sheared off entirely. The fixture would have violently shifted during a high-speed milling operation, shattering the tooling, destroying the spindle, and causing a multi-million-dollar shutdown.
Literally the exact scenario we opened this deep dive with.
Exactly.
Yeah.
Because he investigated the variation instead of trusting the average, a complete catastrophe was prevented by a 20-second turn of a wrench.
That story is the absolute essence of what we call the restorative mindset. The engineer shifted from being a passive observer of a digital dashboard to an active restorer of physical reality.
That's beautifully put.
Good engineering isn't about heroes flying in to fix spectacular explosions. True engineering heroism is aggressively boring. It is the quiet discipline of preventing the explosions from ever happening by listening to the whispers in the data.
Which really brings us to the philosophical peak of our investigation today.
Yeah, let's tie this all together.
If we synthesize the physics of failing bearings, the mathematics of logistics cues, the tail latencies of software, and the control charts of Walter Schuhart, we arrive at a truly startling conclusion about how we manage modern operations.
And it's a conclusion that challenges almost everything we are taught in business school.
It does. The most dangerous, expensive number inside any organization is rarely a metric that is mathematically incorrect.
No. The most dangerous number is the perfectly correct average that successfully convinces everyone in the boardroom that they have seen the whole picture.
It's a comforting illusion.
It's a mathematical illusion. It lulls us into believing that the center of the bell curve, the middle of the distribution, is the entire universe of possible outcomes.
But it's not. We use the average to navigate, but we must use variation to understand. The average ends the conversation precisely where the discipline of engineering should begin.
Because variation is where systems reveal their true, unvarnished character. It's where resilience is actually tested under pressure.
The best engineers, the most effective systems thinkers, they do not celebrate healthy averages. They tolerate averages as a necessity of scale, but they celebrate deep systemic understanding.
They cultivate a mindset, a culture, really, that honors the clues that the physical and digital worlds are generous enough to broadcast.
We ultimately have to accept that while mathematics helps us organize reality so it fits neatly onto an executive screen, reality will always get the final vote.
It always does. And reality does not care about our summaries.
No, it only cares about the physics of the outlier.
Right.
So, as we close out this deep dive, I want to leave you, our listener, with a final instruction for your own professional environment.
Something for them to test this out in the real world.
Exactly. The next time you are sitting in a meeting, whether it is a manufacturing production review, a software sprint retrospective, or a quarterly board meeting, and someone puts up a slide presenting a very reassuring, perfectly green average metric,
Just sitting there looking perfect.
do not ask them if the math is accurate. Assume the arithmetic is flawless. Instead, ask a completely different question. Ask, what disappeared when we compress reality into this one number?
That's the
They
question.
let that question hang in the air. Because that single inquiry has prevented more systemic failures than the most sophisticated dashboards ever built.